Hi, everybody. What we're going to be studying today is something called Pascal's triangle. And Pascal's triangle is used for a number of things. Um, what I want you to do is I want you to look at this pattern of numbers and I want you to think about, what patterns do you see? Like, obviously, we have ones on the outside here. Look what we have in here. We have the counting numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It could go forever and ever. But there are a number of other patterns that emerge here. One of the patterns is that if you look at any two numbers and you add them together, it gives you the number in the next row that's kind of like right between them. Okay, so if you look here, 10 plus 10 equals 20. 6 plus 15 equals 21. So we have a lot of patterns that will show up. One of the other things I want you to notice about this is that we have symmetry. So 1, 5, 10, 10, 5, 1. You slice it right down the middle and you'll have symmetry on the left and the right. Okay, so just some things for you to think about. So what we're going to be using this for is something called binomial expansion. So I want you to think about if I asked you to take a binomial, so two terms, and raise it to the sixth power. What you would have to do is multiply x plus y times x plus y times x plus y 6 times. Okay, and you'd be doing all kinds of multiplication and calculations. What Pascal's triangle will allow us to do is to do that much more efficiently. Okay, so I'm going to show you some things. Okay, I want you to write them down. We're going to talk about some patterns, and I'm going to have you write things a certain way so that the patterns will emerge even more. So first of all, anything raised to the zero power, we know is zero. So when we have this, I'm sorry, oh my gosh, anything raised to the zero power is 1. So I could just write 1 here, and that would be correct. But just for us to kind of get the pattern, I want you to write 1 times x to the 0, y to the 0. Now, the next thing we have is x plus y, all raised to the first power. And again, I could just tell you, write x plus y. Okay, notice I'm spreading it out because we're going to add some things in here. I want you to write 1x to the first, because that's really just x, and then y to the 0. And over here, I want you to think of this as 1 times x to the 0 and y to the first. And what's going to start happening is you're going to start seeing some patterns of numbers. So let's talk about x plus y squared. Okay, that one would look like this. And we would get x squared plus 2xy plus y squared. Again, I'm going to have you write it a certain way where we get 1x squared y to the 0 plus 2x to the first, y to the first. We're adding all these exponents that we usually don't write. Plus, and over here, instead of just putting y squared, we're going to write 1x to the 0, y squared. Now, maybe you see some patterns emerging. 1, 1, 1, 1, 1, 1. Our coefficients on the outside are always 1. Look at our exponents. X to the 0, x to the first, x to the second. What do you think would come next? Hopefully you thought 1x to the third. And how about that y? Y is always raised to the 0 power on the outside, isn't it? Let's go to the outside term over here. And again, 1, 1, 1, we know it's going to be 1. X to the 0, x to the 0, x to the 0. On the outside is always x to the 0. And look at our powers of y. Y to the 0, y to the 1, y to the 2, y to the third. Okay? And I'm just going to help you fill in here. 1 plus 2 is 3. So there's that pattern right there that we just talked about where two numbers add to give you the next. That's actually how we can get our coefficients. It's one of the ways. And over here, I'm going to get the other term. 2 plus 1 equals 3. So we have another term with a coefficient of 3. And that should make sense because look, 1, 3, 3, 1. Now what we will have, instead of x cubed y to the 0, we will have 1 less power of x. So we will have x squared and 1 greater power of y. So y to the first. Moving along, we will have 1 less power of x, so it'll just be x to the first, and 1 greater power of y, so y squared. Notice that, x cubed, x squared, x to the first, x to the 0. Going back here, y to the 0, y to the 1, y to the 2, y to the 3. That will happen each and every time. So I've kind of shown you some patterns here. So let's see if you can write the powers of the variables and their powers. And we'll kind of talk about the coefficients in a second, and maybe you can even do that. So go ahead and pause this video and see if you can fill in x plus y raised to the fourth power. Okay, so I've written out the powers of x here and the powers of y. So notice x to the fourth, to the third, squared to the first, x to the 0. And then the y started at y to the 0, to the first, to the second, to the third, to the fourth. We know that we have a coefficient of 1 here, and we know that we have a coefficient of 1 here. Now, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Okay, so that's one way to get these, and I'm actually going to give you an even better way in a little bit. Let's go ahead and let's do the next one together. Okay, so I'm going to stop writing the y to the zeros. Okay, we know that they're there. We know the first term is 1x to the fifth. Y to the 0 isn't necessary. The next term will be some coefficient, and then it'll be x to the fourth, y to the first, and then it will be some coefficient. X drops down 1, x to the third, y squared, plus, again, we'll get that coefficient in a second. X drops down 1 power, y increases 1 power. Here we go again. X drops down a power, y increases a power. And the last one, we have just y to the fifth, because x to the 0, we don't need to write that. And of course, we know we have a 1 here. Now, I'm going to show you a pattern that's going to be super helpful because, right now we're kind of expanding this. We're writing Pascal's triangle. But later on, I might just say to you, give me x plus y to the fifth power. And you're not going to want to have to write out all of Pascal's triangle in order to do this. So this little shortcut will help you. So here's what we're going to do. We take the coefficient of this term times the exponent. So 1 times 5 is 5. And then we divide it by whatever term number we're in. So 1 times 5 is 5, divided by 1 is 5. And that gives us the coefficient of the second term. So then we do it again. 5 times 4 is 20. This is the second term, so 20 divided by 2 is 10. And we do it again. The coefficient is 10 times 3 is 30, divided by 3 because it is the third term, and we get 10. 10 times 2 is 20. This is the fourth term, so divided by 4 is 5. And then 5 times 1 is 5. Divided by 5 is 1. It gives us that last term, or that last coefficient. So you can see that's a nice kind of quick way to be able to get those coefficients. Okay. So I'm not gonna actually do the sixth one because it will take a little while. But what I'm going to do is I want to talk to you about some of these patterns that we've noticed, some patterns, some things that I've talked about. So first of all, the rule that we just talked about, perhaps the most important rule, is this one. If you take the coefficient of one term and you multiply it by the exponent of that term and divide it by the term number, that will give you the coefficient of the next term. That's going to probably be the most important thing in terms of our patterns. Okay, and we'll get to that. Another thing I want you to notice, if we were to scroll up here, I want you to notice that, for example, this exponent is 5. So here we have 5, and then remember y would have been to the 0, so this adds up to 5. 4 plus 1 adds up to 5. 3 plus 2 adds up to 5. 2 plus 3 adds up to 5. 1 plus 4, and so on. So the x exponent plus the y exponent will equal n, which is the exponent of the expansion. Exponent of the binomial being expanded. Okay, that's the n value, and we'll get into that in a little bit. Okay, something that we talked about too was that the x exponent decreases by 1 with each term, each successive term, and the y exponent, or the second term's exponent, increases by 1. Okay. And something else, just to make sure that you're kind of on the right track, is that when you're expanding any one of these, for example, this exponent here was 5, so our n value here is 5. That will result in one more term than the exponent. So in other words, 1, 2, 3, 4, 5, 6. Okay. So you'll always have one more term. So that's something that we have to, right? It's important because you might miss one. Okay. So expanding x plus y to the n results in n plus 1 terms. So one more term than what that n value was. Okay, and there were some other things that we talked about, but that's the general idea there. So that looks kind of messy. Okay, probably looks a little scary, but it's just the formula. It's just, with all the variables and showing how n decreases by 1 and y will increase by 1. Okay, n minus 2, n minus 3, and so on. So it's really just another way to look at this. Okay, so what we're going to do right now is we're actually going to do one problem together. And we're going to expand x plus y to the 7th power. Now, again, you wouldn't want to have to write the Pascal's triangle all the way down to the 7th term, or when n equals 7. So what we're going to do is we're going to use some of the rules that we just talked about. So first thing I like to do is I like to put up just a little line there because I'm going to fill in all of my coefficients later. And what we know is we have this term right here raised to the 7th power, and the second term raised to the 0. I'm not going to write that next term. Then we have a coefficient, and the x exponent will decrease. The y shows up. Y to the first, I'll put it this time. Leave a spot so we can do the exponent, or the coefficient. X to the 5th, y squared. Okay, and so on down the line where you're decreasing the x and increasing the y. And remember, these should always add up to 7 because we're expanding to the 7th power. Okay, so go ahead and finish that. This one's a tight one because it's a lot of terms. Okay, and hopefully so far so good. Now, we knew something right from the start about our coefficients. We knew that this was always going to be 1 and that the last term had a coefficient of 1. Now, let's go ahead and use that rule that I taught you, which is the coefficient times the exponent divided by the term number gives us the next coefficient. So 1 times 7 is 7, divided by 1 is 7. Next up, 7 times 6 is 42, divided by 2 is 21. Now we're going to keep going. 21 times 5 is 105, divided by 3 is 35. Okay. 35 times 4 is also 10. What is it? 35 times 4, 4 times 30, 120, 130, 140. Sorry, 140 divided by 4 is 35. And now do you notice that we're starting to get some symmetry here? So next one down the line will be 21. Next one down the line will be 7. And that's it. We're done. Okay, we're done with that one. Hopefully not too bad. Let that sink in for a second. I'm going to do one more example. This one's going to get a little bit messier though, because look at example 2. We now have 2x and we have minus 3y. So that does change things a bit. So we have to think of this as our first term and 3y as our second term. So we will have a blank, which we know is going to be a 1. Now watch this. We have all of 2x raised to the 4th power because our n value is 4. 3y to the 0. Plus, you leave a blank. We're going to have 2x raised to the 3rd power. And I put negative 3y raised to the 1st power. Okay, you might want to think of this as plus and negative. We'll talk about some things in class as well, but different ways we can do this. Keep it going. We leave our blank. We have 2x squared negative 3y squared plus 2x to the first negative 3y cubed. And of course, our last term, which is not going to have 2x, it'll be 2x to the 0, so we're not writing it anymore, negative 3x to the 4th. So this one's going to be a little bit more complicated, but as of right now, the rules are the same. We know that there's a 1 here. We know that there's a 1 here. We know that there will be symmetry on the spot where I put for the coefficient, okay? So 1 times 4 is 4, divided by 1 is 4. 4 times 3 is 12, divided by 2, because it's the second term, is 6. And now look, we have a little symmetry here. 1, 4, 6, 4, 1. You cannot leave your answer like this. We need to clean this up. So what I like to do is I like to go ahead and clean up each value that's being raised to the exponent and then do one more step after that. So 2x to the 4th, well, 2 to the 4th is 16, and then we just have x to the 4th. Plus, I would personally bring down that 4, and now we have 2x cubed. Well, 2 cubed is 8, and we have x cubed times negative 3y. Keep it going. Bring down the 6. 2x squared is 4x. Negative 3y squared is positive 9y squared. Keep it going. Bring down that 4. No math to do there. We just have 2x. And then we have negative 3y cubed. Well, negative 3 cubed is negative 27. And then we just have y cubed. And the last one, we have that 1. I'm not going to write the 1. Negative 3 to the 4th power is positive 81. And then y to the 4th power. Now, I want you to stop this video. I want you to clean all of this up and then check back with me and see if we get the same answers. Okay, so let's take a look here. So a couple things happen when we do this. So first of all, you'll notice the variables x to the 4th, y, x to the 3rd squared. Okay, so things are still happening here. Our symmetry goes out the window with regards to our coefficients. Okay, because once you have a 2 in here and a 3 in here and it's negative and all this, like things just, we had symmetry up here, but once you actually do the calculations, you lose that symmetry of the coefficients. I do want you to notice that because we had subtraction here, watch what we have. We have a positive term, a negative term, a positive term, a negative term, and then a positive term. So that alternating will happen. Something to think about. Okay? So listen, what I want you to do is I want you to just let this sink in. Maybe try to do this one again, see if you can do it on your own, or try to do the previous one again, see if you can do it on your own. And we will pick up in class. Have a great day, everybody.